Well,
Good afternoon to one and all present here. It is an honor and privilege to introduce our esteemed guest for the day, Professor Vadlamani Ravi Garu. Dr. Ravi is currently a professor at the Institute for Development and Research in Banking Technology, Hyderabad, where he has been serving since 2005. He heads the Center of Excellence in Analytics, now called the Center for Artificial Intelligence and Machine Learning, India's first such center in the banking sector. He holds a PhD in soft computing, jointly from Usmania University and RWTH Aachen, Germany, and also holds degrees from IIT Bombay and BITS Pilani. He has previously served as a faculty at the National University of Singapore and worked as an assistant director and a senior scientist at prestigious national institutes like CBRI and IICT. With an experience of over 37 years in research and teaching, his expertise includes soft computing, data mining, big data analytics, deep learning, adversarial and explainable AI, federated ML, and reinforcement learning. Dr. Ravi has published over 280 referred papers, co-edited several international handbooks on big data analytics, and has a H index of 49 with over 13,300 citations. He has successfully led major projects funded by DST and Canara Bank, focusing on fraud detection and adversarial machine learning in banking. He has guided 8 PhD scholars, supervised over 75 postgraduate projects, and examined doctoral theses for IISc, IIM Calcutta, and other premier institutions. In 2024, he was ranked among the top 1.03% of AI and image processing scientists globally and 72nd in India by Research.com. He also serves as an advisor to RBI committees and a consultant to National Bank for Agriculture and Rural Development, Securities and Exchange Board of India, Insurance Regulatory and Development Authority of India, and several banks. He will be delivering keynote session on the topic feature subset selection for streaming data using parallel evolutionary algorithms. We are truly honored to have him with us today. Please join me in warmly welcoming Professor Vadlamani Ravigaru to address the keynote.
it works. Is required. Which one do you prefer? No, which ghost is? Huh? Okay. Um, Good afternoon, everybody sitting here. Thank you very much for inviting me here to deliver a keynote in this prestigious ICACCES conference 2025. I'm very happy to deliver the talk titled Feature Subset Selection for Streaming Data Using Parallel Evolutionary Algorithms. Okay. This is the outline I have. We give brief introduction to the feature subset selection problem, briefly touch upon the literature review, address the gaps and challenges, and in the process, two different frameworks that we developed for feature subset selection, one for data streams and the second for feature streams. And finally, we have some conclusions. Now, just to get started, what is the motivation for feature subset selection? Which is, I will believe, a very important pre-processing step in the entire, you can say, life cycle of machine learning projects. Whenever we solve problems having large number of features or variables, it is but natural to assume that all of them are unequally important. I repeat, all of them are unequally important. If that were so, who on earth is going to tell you what are the important variables and which are not? So that we can filter out unimportant or useless or redundant variables and retain the most important variables for downstream applications. What downstream applications I'm referring to? It could be classification, regression, or association rule mining, or even clustering for that matter, or even outlier detection. These are the primary tasks of data mining. This is not something new to the fraternity of machine learning practitioners, students, professors. What is new over here is how to do all this problem of feature subset selection in the context of, in the paradigm of big data. Then a lot of challenges you will come across, and that is what we addressed here very successfully. And that is the core of this keynote. Fine. So if you look at the advantages of feature subset selection, the advantage of InMerge, I would say, first and foremost, explainability becomes very easy. Explainability of the model underlying. It helps build less complex models. Here we refer to what is known as Occam's razor. You can Google it later. Or from the statistical parlance, we say parsimony aspect of the model. Parsimony means frugal, the English meaning. You should develop and identify those models having very least number of parameters, trainable parameters. I'm not referring to hyperparameters, right? And then it increases human comprehensibility. So these are the advantages that are accrued from feature subset selection, which is an important aspect of data pre-processing stage of data mining projects. And having said that, primarily there are three different approaches to feature subset selection. One is filter, then wrapper, and finally embedded. In filter-based approaches, we simply look at the strength or otherwise of the individual features and select the important features thereof. A lot of methods are there coming from statistics and machine learning family. Then you got embedded methods. As the name suggests, while the model is getting built, it could be a classification model or a regression model, the variables get selected and dropped off. Some of them will be dropped off automatically without your intervention. That is the beauty of these models. Examples could be your lasso regression, decision tree. Support vector machine also comes with such kind of feature where you have to have an add-on algorithm which is called recursive feature elimination, RFE, so on and so forth. And rough set based methods, they are eminently suitable for building feature subset selection, classification, as well as rule induction, all in one go. Only these methods have possessed that the kind of property, and nowadays not many people are working in this domain. I feel sad about that. And they are scalable despite that fact. So that is a gray area if somebody wants to step into that with other additions. I will talk about it later. The primary core of this keynote is wrapper. Wrapper, as the name indicates, you have got some core in between, and surrounding that there is a wrapper as an English meaning. So if we get into that deeply, maybe in subsequent slides I'll talk about that. But what are the advantages? Advantages are immense. What is not available in filter based or embedded methods, where you can actually factor in the interrelationships between variables and features, that is captured by wrapper based methods, and that is the beauty. And in the process you have to pay some price. That price comes in the form of computational complexity. No problem. Essentially, in wrapper based methods, the entire feature subset selection problem is formulated as a combinatorial optimization problem. Madam, I'm leaving the slides here. Okay, there are many things that I speak which is not there in the slides, that you can note. So how is this combinatorial in nature? For example, if you got n features, the number of subsets that you can formulate out of that is 2 to the power of n minus 1. And what is that one we are excluding? The subset where none of the features is selected. That is meaningless. That means one feature from the features, the set of combinations, taking one feature at a time, two features at a time, 3, 4, etc. n. That comes to the power of n. But minus 1 we are excluding because we want to exclude that subset having no features. I just give numbers here, which is mind-boggling. If the number of features is 10,000, and normal machines cannot work, the sequential algorithms will fall flat. You have to make them scalable. The existing technology does not afford. Therefore, we take the help of evolution computations, computing algorithms, and on top of that, we make them parallel. Lots of applications are there in banking and other domains. In the morning session, we were talking about cloud burst, and Professor D.N. Rao talked about, the weather forecasting. Even Dr. Pandian talked about it. What does that mean? It comes with a lot of variables. And the very fact that it is basically chaotic in nature, apart from randomness, it throws a lot of challenges. Only some countries are able to do weather forecasting as accurately as possible, not everybody. So in all such cases, apart from these cases, where you have to grapple with huge number of variables and then weed out unnecessary, irrelevant, redundant variables. Pick up only the important ones. And that is where this particular work helps very much. Now, a small primer on evolution algorithms. At a dichotomy level, at the topmost level, we call them as meta heuristics. But then, within that, you have got two categories. One is point solution based, another one is population based. Within point solution based, you have algorithms like simulated yielding, threshold accepting, taboo search. On the right hand side, on the population based methods, we got differential evolution, genetic algorithms, particle sum optimization, anti-colony optimization, so on and so forth. The same kind of setup of evolution algorithms has got further trichotomy, in the sense that you can actually look at, from solve the problem from a single object to environment. Then you have got all these algorithms coming in under that category. Then we have got multi-objective. Then you have got NSGA2, due to my close friend, collaborator, Professor Kalyan Deb, and several other algorithms are there. And the last one, many objective. Anything goes beyond 3 objectives, they call it a many objective optimization problem. So basically what happens here is population encoding. As I told you, it is combinatorial in nature. Here, the string, there are, let's say, 5 strings here. What this means is, and F1 left to F up to F6, 6 features are there, just for illustration. 1 means that particular feature is present, 0 means particular feature is absent. That's simple notation. Now, given this combinatorial nature, just to tell you that all of them will be kind of evolving as the algorithm progresses. That is the basic nature of evolution computing algorithms. And when you converge, when the algorithm converges, we'll be having a set of algorithms, set of solutions, or you can say feature subsets, which are equally good, more or less equally good. Now let me talk about big data. All of us heard the word big data. We learned that in the class and all that. Some may be doing research also. But then it requires minimal introduction here. Big data is characterized by 5 V's. Internet is, flooded with 10 V's, 7 V's. Don't look at all those things. You'll get confused. 5 V's is good enough to succinctly capture the essence of big data. It is called voluminous aspect. If any data is voluminous, we call it big data. Then got variety. That means it has got structured, semi-structured, unstructured data. Then velocity comes, data comes at a very rapid pace and disappears. Examples are cloud burst, the other examples that we gave in the morning. Then I got veracity. Is the data source coming from a certain source or is it a fake source? How do you assess that? That aspect is also falling in big data. And finally, value. In many applications, we may be inundated with huge amounts of data, but then only a fraction of that will have a potential value in that. Maybe a scientific value or a business value or whatever. And who on earth is going to tell you where that subset of data is residing? That is, for that again algorithms are there. So together these 5 ways are capturing the entire essence of big data. In normal practice, we come across the first 3 ways: volume, variety, and velocity. In this specific task, the two project papers I'm going to present here, we talked about only volume and then velocity. Variety is something that can be added on very easily. So why scalability is important? As I told you, whenever you are encountering huge number of variables or features, the complexity increases, the convergence time, becomes longer and longer, and you will be ending up with suboptimal models. And then if you want to explainability is a big thing now for AML applications. If you can't explain your models, then the end user will not be taking up your model. This trend started in 1988. Stephen Gallant was the first person to address this in the form of neural networks because medical community rejected it. And bioinformatics, a lot of applications are there. Then we talk about parallel evolution algorithms. So when we talk about parallelization, there are multiple ways that, because just like neural networks, evolution algorithms are also inherently parallel. So by design, not by accident. Therefore, they said, if they are inherently designed, by design they are parallel, then why don't we parallelize them through a process? And that is where our entire Hadoop ecosystem comes into play. Now Hadoop is getting replaced by Spark cluster. We take elements of Hadoop here and there, for example, HDFS system, file system, but then Spark is gaining a lot of traction and a lot of popularity because of flexibility of in-memory computing, so on and so forth. Again, within that, there are two different approaches. One, you could go for a master-slave model. You can take one machine and everything, let me tell you, is horizontal parallelization, not vertical. That means you don't have to have a GPU. That's what I was suggesting some of your faculty members some time ago. You can set up several yarn clusters here, Spark clusters, and start solving very complicated problems. All that requires is a set of machines. It could be as simple as maybe a laptop with 16 GB RAM. One of them becomes a master, remaining becomes slave models, slave nodes. Then you have to go set up this master slave model. Otherwise, you can go for island model also. That means HDFS allows you data parallelization, but we need to do process parallelization. And that is where we pick up algorithms which are inherently parallel and then make them actually parallel computationally. That is where research element is involved. Okay, and lot of scope is there even now. So we produced 2 PhD theses in this area. So you have got multiple alternatives like OpenMP architecture, MPI, CUDA, that is for GPUs, and then Hadoop and Spark for the CPUs. Okay, if you go for Hadoop and Spark kind of approach, we call it as horizontal parallelization. If you go for CUDA, we call it as GPU, that is vertical parallelization. In some of the most complex problems nowadays, people are going for a hybrid. That means a kind of horizontal parallelization where you actually have multiple GPU processors involved, not just CPU processors. That is warranted by the complexity of the problems. And in this particular case, we went for Hadoop and Spark. That is what is the remit of our project. And these are an important slide just to tell you that traditional optimization algorithms are sequential by design. You can't do much about it, and hence they are not scalable. But then evolution algorithms, as I was mentioning multiple times, they are parallel by design and they come up with a lot of advantages, right? And therefore, look into the fourth quadrant, that is the focus of research here. We parallelize them using HDFS and Spark kind of architecture. The challenges involved here are significant computation time when the number of variables is large. Extant wrappers are not scalable because they are not amenable for big data. They are not designed to look at the voluminous aspect of the big data, variety, and then velocity. Therefore, we have to resort to evolution computation. And designing new wrappers for obtaining more potent feature subsets in terms of achieving higher AUC, higher relevance, lower redundancy, and lower cardinality. What is cardinality here? Cardinality plays a very important role. Cardinality, just remember our set theory days when we were introduced. The number of elements in a set is called cardinality. So you should have as high AUC as possible, but at the same time as low number of features as possible in the feature subset. If we can achieve that twin objective, that's fantastic, and that's what we achieved here, both in a single objective framework as well as multi-objective framework in this particular thesis. But only an element of that I'm presenting here. So the first project that we are going to project here is novelty detection and feedback based online. Please remember here, online means streaming data. This is what I was talking about in the morning. Feature subset selection for data streams via business benefits and customer benefits can be accrued, but not everybody is doing this. That is my worry. Okay. And then to analyze these data streams in real time or near real time. This is a very important thing in cybersecurity, because these kind of, cyber fraudsters, you can call them a cyber terrorists, they may be as intelligent as you and I, but they are much greedier than you, all of us. And they want money yesterday, not their money, not legally obtained, somebody else's money. That separates fraudsters from us. Okay. So in that is the case, then if they are continuously on the prowl attacking you, trying to attack you, your machines, your network, infrastructure, etc., then we should be equipped with streaming analytics framework. That is what I advise all the banks. Some of them are actually listening and that started implementing that kind of thing. So the major challenges here are latency, and then fault tolerance, scalability, identifying and tracking abrupt changes in the data. That is what we call as data drift, concept drift. That also should be monitored, etc. Traditional algorithms cannot do all these things. Therefore, we have to take this path of research. Consequently, incremental learning algorithms. There is a difference between online and incremental learning algorithms. I'm going to discuss that in a while. Before we do that, when we talk about streaming analytics, streaming can happen in 2-3 ways. Data samples can come in stream, but number of features are fixed. That is one case. In another case, number of data samples is same, but features are getting added. The columns are getting added. One on the row side, another on the column side. The third one is a hybrid of both. And unfortunately, in our current problems, scientific and business and other problems we are facing with, we have all these 3 cases arising. Then we can't help but start developing models there. But if you are developing models there, you have to factor in all these challenges and then address them. And that is where this research is actually helping. So UPI interface, all of us are using UPIs. So people tell me that there are many frauds happening in UPIs. We are very lucky if we are not encountering fraud, but if we are kind of fraud is perpetrated in our transaction, we know how kind of stress it gives, financial and other emotional stress. Fraud detection versus with respect to all other financial transactions, cyber attacks, log analysis. In all these cases, streaming data analytics is very, very important. Incremental versus online. Online feature subset selection algorithms minimize the space and time complexity. Please remember, because they are addressing the data in real time. And they're specifically designed for streaming context. On the other hand, they don't have incremental nature of learning. What is incremental? When we say incremental FSS algorithms, FSS stands for feature subset selection. They exploit the accrued knowledge so far, and they want to make the algorithm learn the new characteristics if only new characteristics are available in the new stream of data. If it is discovered through vigilance tests, there is no new information is available in the data streams, that data stream is kept just like that. The training algorithm is not invoked. So this is where we made a contribution here. I'm going to talk about that. So basically the data process in data streams is voluminous and there is a high velocity. Therefore, we applied a computational lightweight evaluation algorithms. Please remember, if you are working in or if you are maybe familiar with evolution algorithm kind of family of algorithms, some of them are extremely complex. For example, bacterial foraging algorithm. It has got 10 hyperparameters. PSO, particle swarm optimization, only 2 hyperparameters. GA has got 4. Differential evaluation has got 4. So the more and more hyperparameters you have in the algorithm, whether it's machine learning or evolution computation, it gives you more flexibility on one hand. It also gives you a lot of headache on the other hand, because you have to perform grid search in order to identify optimal hyperparameter combination. So that is where we have chosen very lightweight at the same time without compromising complexity, accuracy. Incrementally training the algorithm where we preserve the knowledge gained thus far. Whichever knowledge is gained in terms of, let us say, important features are selected, we don't want to throw them away just because a new stream of data has arrived. But then we want to assess what is the novel information available in the data. If it is really available in the new stream, then and then only the algorithm will be actually working on top of that. Otherwise, the stream gets ignored. This beautiful trick we have done, and you see the results. And this is where we borrowed the concept of novelty detection, vigilance testing from adaptive resonance theory. Some of you may be aware, ART1, ART2, second generation models, Carpenter and Grossberg paper, 1972. Okay, beautiful thing. Just because deep learning has come, people are ignoring it. I said, I'm not that kind of guy. Old things I will not discard so easily, whether in personal life or professional life. I keep using them repeatedly and tell the whole world, hey, look, this is the use of this. People have to be immersed, okay? So robust mechanism devised to detect novelty in every incoming stream, thereby reducing the number of retrains. The algorithm should be retrained whenever it is necessary, otherwise not. Without significantly sacrificing the classifier's performance. That is a very critical point. And thereby, you address the latency on one hand and accuracy on the other hand. Okay. And in addition, underlying EA has to be is parallelized, and moreover, the severe data imbalance. So most of the data sets that we come across are highly unbalanced. That also is addressed here in this particular study. So this is the architecture. Incoming data streams are there at regular intervals, and then beauty here is using a concept called D-stream. I do not know how many of you are familiar with. D-stream is a concept in Spark using which you can make the static data simulate like a streaming data. Few lines of code is required, that's all. And there is a hyperparameter called latency. You can fix the latency. Here we took 240 seconds as the latency. 240 seconds we took. You can choose anything what you want. Accordingly, you can see the results differently. That means whenever streaming data is available, we can apply our research here. If it is not there, we simulate that showed behavior. That's the beauty. So this architecture, you got, HDFS storage is there for the driver node, and these are the worker nodes. Data is getting partitioned through HDFS cluster. And then these are four things that we did. We handled data imbalance through SMOT. All of us know synthetic minority oversampling technique. Then vigilance test, this is where we made some contribution. And then of course fit test tolerance, and finally wrapper. Fine. The assumption we made here is that there are some positive class samples in the first stream, without which you can't process this algorithm at all. Some minimal number of positive samples. Positive class means fraud. It could be churn. It could be cyber attack. It could be NPA. That is, default data. So such kind of examples I'm giving where positive class is done, where we are actually interested in making the predictions. Negative class is a huge number of genuine or normal transactions where we don't have any interest. Okay. So that is assumed to be there. And of course, balancing is done by SMOT. Then talking about vigilance test, we went for Frobenius norm and modified it. Frobenius norm, as some of you may know, if you want to compare two matrices, square matrices, Frobenius has given a norm. A matrix has got several norms like. This is one of them. And then what we did here is, we took the variance covariance matrix of the existing stream, compare this with the variance covariance matrix of the existing stream with the new stream. If there is a significant difference between the two as measured by this number, then we say that new stream has got some statistical information, new information. If the significance is less, difference is less as indicated by threshold, which is predefined, then we say this stream doesn't have new information. Throw it away. We ignore it. We don't want to overload the algorithm. Okay, that is the beauty. That is the first method we have done, which is statistical in nature. We did not stop there. We looked at the data from geometrical perspective. This is where we took the help of cosine similarity. Cosine similarity of the median. Cosine similarity of the median vector of the current stream versus the next stream. We took, and if this is small, again defined by threshold, predefined threshold, then we say that there is no novelty, geometrically speaking. It is pretty close to the existing one, therefore ignore training. So these are the two things put together, and then fourth one, we went for, this one, feedback based on fitness tolerance. If there is not, is no significant difference between the AUC, area under ROC curve, of the current stream followed by the previous stream, if that is very small, then there is no need to retrain. Putting together all of them did the wonders for us. And then and finally we have the wrapper. Wrapper is implemented this way, as I told you, the master slave model. And this is the architecture, just to tell you the scheme, how it works. At the time step 0, you have got no training data. Time step 1, you have got training data, S0. Immediately PSO1 is invoked. PSO1, the 1 stands for first instantiation of PSO, particle sum optimization. And we did this multiple times. Let us say we illustrated till time step 6. In the first case, we just compute this test PSO1 on the streaming data, which is S1, and then report the results. We don't do any novelty detection. As and when the new data comes in from the third stream onwards, novelty detection is performed. That is the other side. Okay. So proposed algorithm is this. Okay. It is proposed in literature. Not much traction is given. We somehow resurrected this algorithm from nowhere. I should credit my student for this. It's called bare bones. As the name indicates, PSO is very lightweight. All of us know. Within that again, still lightweight. It has no hyperparameters at all. That is the beauty. And then we tested it thoroughly. It did not disappoint us. Therefore, we took that, and then for the solution updation, they used Gaussian distribution of, let's say, mean and standard deviation. 2 parameters are required. That is computed by P best plus G best divided by 2. That is arithmetic mean, and then absolute difference between the two as the variance. That's it. That is what the literature said in bare bones. We said no, we will not go with this. We go with logistic distribution. All of us know sigmoid, right? Sigmoid is what? It is giving us S curve. That is cumulative distribution function. But if we take the derivative of that, it is exactly S curve. But this S curve is just similar to Gaussian, but then with heavier tail. Heavier tail, this black one is the logistic distribution. It did fantastic job for us, more than the Gaussian one. So these kind of new things, new innovations we developed, and then we got these hyperparameters and 4 data sets we tested, first 2 are from bioinformatics, and then second 2 the epsilon and then malware. These are malware data sets from cybersecurity. Look at the results. So BPSO, that is bare bones PSO, 110. OF1 means objective function 1, which is cardinality. Objective function 2 is AUC. So as I said before, our AUC should be as high as possible. Cardinality should be as low as possible. So that is what we tried to do. PSO 1.3, PSO 4.2, these are all the variations, okay, available in literature. We needed to do that because every time you propose a new algorithm, you have to compare with baselines. Please remember that. And these are our baselines. So BBPSO, this is binary PSO, bare bones PSO, hyphen L. L means logistic. Then L plus threshold neighborhood search we did, and that did the trick here. So this whatever is highlighted here has got least cardinality and then highest AUC. With this for momentum data set, this for uterus. Again, IEEE malware. So these data sets have got 10,000 variables. And then number of transactions is, number of samples is pretty running into lakhs in some cases. So high dimensional, high voluminous. So these are the number of retrains versus novelty detected. These plots, we gave. We got a lot of insights from this. More details are available in the paper. So in summary, bare bones PSO driven by logistic distribution plus threshold neighborhood search consistently outperformed all algorithms by yielding optimal solutions. Optimal with respect to higher AUC, lower cardinality. Overall, cosine similarity and modified Frobenius norm. These two vigilance tests outperformed each other in 2 data sets each. And results demonstrate that across all data sets, the proposed framework yielded higher mean AUC with less processing time. That is the beauty compared to the baselines. So therefore, now it is ready for any kind of real-time setting. Whichever problem you pick up, we can use it. So the second one we did not stop there. Immediately I challenge my student to do the other one also, which is keep the number of samples fixed, but features keep on coming in a stream. This is the exact transpose of the problem. We did that. And yeah, the essentially same thing, developing efficient streaming evolutionary algorithms framework for feature streams. Earlier it was data streams, please remember. To the accomplish the same task, FSS maximize the AUC, single object environment. And these are the other applications. Lot of space applications, etc. Edge detection, texture image in image processing, genome sequences again in bioinformatics, so on and so forth. Even in drug, drug modeling, drug manufacturing, medicinal scientists, they require this kind of stuff. The contributions are like this: develop novel wrapper-based framework that is suitable to handle high voluminous feature streams arriving at high velocity. Introduce incremental learning. Here, incremental learning is required. I'll tell you how we did. Propose two vigilance tests again, just to weed out irrelevant variables and then relevant variables. That means there is some information, important information they have captured. That means they are more discriminative compared to other features. Therefore, we retain them. That is from the spirit of elitist mechanism, elitist principles in evolution computation. Those variables continuously went through all the iterations without getting replaced. That is one thing. So relevance is something that we captured using mutual information. Redundancy, again, we took the help of cosine similarity. So one is a probabilistic approach, other one is a geometric approach. These two we did in the feature streams. For data streams we did statistical approach followed by geometric approach. Please see how we have captured from looking at the same data from multiple dimensions. That's very, very critical. I want you to look at these things closely so that you can implement your projects later on. You can extend it. Fantastic. So this is the kind of architecture diagram. Just to give you an illustration, population size looks like this. Basically, the rows are nothing but the solutions, columns are nothing but the features because it's a population-based approach. But incoming stream has got 3 more features added. So that then the population size gets expanded column-wise. Row-wise, it remains the same. That is the assumption we made. Yeah. So invoking vigilance tests, which is relevance-based, based on mutual information, redundancy based on cosine similarity, followed by identification of elite features. Just now I mentioned how we did that. And we went for island-based approach for parallelization of the evolution algorithm. Incremental learning is required here as well, and we did that. And of course, tolerance-based feedback. Tolerance means if there is only minimal change in the AUC, that means the incoming features stream is not contributing much. Therefore, despite being detected as novel, if they are not contributed, let us throw them away. Ignore them. Go for it for the next stream. So this kind of decision making we had to do. Otherwise, it becomes unwieldy problem. Okay. So in conclusion, online FSS solved for streaming data involving insert streams as well as feature streams. BBPSO is extended to BBPSO L. L stands for logistic distribution. Vigilance tests are proposed by us using statistical domain as well as geometric domain. Otherwise, probabilistic domain come together with the geometric domain in the two cases of data streams as well as feature streams respectively. Threshold neighborhood search actually looked at important changes in the neighborhood of the current solutions and invoked them. D-streams feature is used to simulate the streaming behavior for the static data. Please remember, we can use it for streaming data also as it is available right now. Application domains are cybersecurity, bioinformatics problems, and many others, even weather forecasting. So this paper got published in the Core ranking conference in Australia, that is GECO. In 2024, my student went there and presented in Melbourne. By the way, he is a student of IDRBT and NIT Warangal. We have a collaboration with them. You can see the other guide being Professor Radhakrishna. Then the second one, as a late breaking abstracts they call it. They asked us a germ of an idea. If the germ of idea, again that goes through review. If they accept it, then they publish like this in the compounding proceedings. But it went there, we only gave the idea approximately at a high level. At a 4-page abstract, they published it. Then the extended version is published here, which is having impact factor 8 and above. So these were feature streams. So just going back, the data streams got published, got GECO, Core conference, and subsequently this one, only the idea. But the actual implementation, what I showed in the second one, which I didn't get time to present here, that is for feature streams. There is having Q1, that is a quartile 1 journal. Nowadays they are looking into quartiles, Q1, Q2, like that. So these are the three papers we got this, and then yes, these are all the references. I hope it's useful to you. It has opened up some ideas. I'm happy to take some questions. Thank you very much. Good question. They are they're tractable, sir. They're not logarithmic. They're polynomial in time. Data is parallelized by HDFS by design, but process parallelization we did here. Excellent question. I was waiting for this kind of question. So when we go for master slave model, each of the nodes, worker nodes, they are run a kind of miniature version of PSO. With smart, because data is getting partitioned across all worker nodes. With that miniature partition, it works a miniature version of PSO. At the driver node, all of them get aggregated. So that is a process of Spark. We don't have to worry about that. Beautiful question. Very happy. Here we used good question. Here we used two bioinformatics datasets available in the public domain, and of course these are remaining two are from available in Kaggle. That is cybersecurity, malware detection. Malware detection has got huge number of features. There is another set called Microsoft malware that actually gave some data quality problems, so we just dropped it. Otherwise, DDoS detection data set is there. We could do that here. But the problem is, sir, I tell you, the challenges are very simple. When the number of samples is very large, number of dimensions is less. Number of dimensions is very large, number of samples is small. We face this kind of issues, especially in bioinformatics. Number of dimensions is very large, running at 10,000 like that. Number of samples is not more than 1,000. That is, each sample is a human being. Okay, okay, genetic profiles, etc. But in cyber security, things are different exactly. But then there are other kind of use cases, domains where this kind of string is very much useful, especially UPI transactions, where both are very large. Uh, sorry, data, NPCI holds that. They are the people who are running it. Even I can't lay hands on that. If we have MOI with them, it's very difficult to get their data. Because, if any small thing happens, there will be a national furor. Synthetic data. So that is where GAN helps you. Generative adversarial neural network. Now, synthetic data is a huge market now, running into billions of dollars. Wherever privacy concerns are there, confidentiality concerns are there, people are going for synthetic data generation. And unlike earlier days, now using GAN, its variants, you can exactly replicate. Deepfake is one example for image data. For tabular data, you can generate very well. Any questions from student community? Is this something new that you heard, or kind of routine thing? Did you learn anything new, or you don't want to speak? There is A, B, C, D. Option D. Faculty community who registered for PhD. Any question, please? There's a lot of scope out there in streaming analytics. Still, people are exploring various ways. What I suggest is earlier also unsolicited advice. Always give this wherever I go, and VNR Vignan Jyoti I can give always. Okay, I feel it is a privilege. Please set up clusters, yarn cluster within your department, within the whatever lab you call it, and let the student dirty their hands how to set up, because these kind of skills are not taught in the market anywhere, not even stupid Amirpet institutions. You are the best people to do it, because these are the skills required in the market. In the interviews, they are bumped with these kind of questions and they don't know how to answer. You get the point? So take that as some kind of maybe a lab for 20 marks or whatever, and then in the process you are opening lots of new doors of research and application. With quantum coming in a big way, you cannot ignore this, let me tell you. And there will be a lot of learning for faculty also. Any questions? Expected more questions. That's that's what I told. So malware is one example I gave. We also worked with DDoS detection. Data sets, very good question. So we took this data, okay, IEEE malware, Microsoft malware, they're available in Kaggle. For DDoS detection and then ransomware detection, you have to go to Canadian website. It's the public domain. We are download data from there only. But you have to do a lot of pre-processing. Okay, you can do that. So if no questions, thank you very much for the wonderful opportunity given to me. Thank you, Brahmandra Reddy Garu and Baby Madam, for having invited me here to share my thoughts and experience. I wish a grand success to the conference. I would love to be here for all the presentations because I also want to learn new things and give suggestions. Unfortunately, my time does not permit me to be here for more than this. Thank you very much once again.
Thank you, sir, for enlightening us on future subset selection, its various approaches, and the role of evolutionary algorithms in optimizing this process. Your insights not only deepened our understanding of the theoretical concepts but also highlighted their practical applications in the real world machine learning tasks. We truly appreciate the clarity with which you explain complex ideas. Now, all are kindly requested to have their lunch near E block, room number E133, and assemble for paper presentation by 2 p.m. in E138.